Okay, welcome to lesson 4.
I'll take my chances in a mystery wall. Oh, glory of glories. Oh, heavenly testament to the eternal majesty of God's creation. Holy macaroni!
And just like Homer, we are going to bravely step into the third dimension here. So, every problem that you've been dealing with so far has been what's known as two-space problem, a 2D problem. It exists in the vector field called R2 or R squared. Basically, it's called R2 because there are two real number lines stacked on top of each other at 90 degrees. So the x-axis and the y-axis, they're both number lines on the real numbers. So everything we've done has existed in 2 space. However, now we're going to start to think about 3 space, and that is 3D diagrams. So we're going to have an x, a y, and a z axis. And the way you typically draw this is like that, to sort of give it some 3-dimensional representation of a 2D thing. And so x, this is the y, and this is the z axis. So normally you just draw this just showing the positive sides of the axes, but they do extend into the negative, so we get sort of that going on if you want. But I usually don't have the negative side showed in my diagrams unless I need to for some reason. So in 2D, you have 4 quadrants. In 3D, now you get 8 orthants. So they're called orthants. There's 4 on top, 4 with positive z's, and then 4 on the bottom with negative z's. In 2D, if you have a point on the x-axis, you know that its coordinates are some number and 0 for y. And if you have a point on the y-axis, you know it's some number for y and 0 for x. In 3 space, you get something similar. If you're on the x-axis, you get some number for x, and both of the other 2 components would be 0. And for the y-axis, something for y, both of the other things would be 0. And if you're on that z-axis, 0, 0, some number for z. The other 2 are 0. So hard to draw stuff in 3D on a 2D page, at least for me. But if you want a visualization of an X, Y, and Z axis, you can look at sort of the bottom corner of the room that you're in. So sort of the baseboards running along the wall would be the X and the Y axis, and then the corner going up the middle of the wall, or between the 2 walls, would be your Z axis. So that's a way to visualize it. So we have 3 axes in 3 space. We also have 3 main planes. So we have what's referred to as the XY plane. And so if you have a point on the XY plane, normally it's actually written XY plane. The key thing here, if you have some point on the XY plane, is the x and y can be numbers, but the z has to be 0. So in fact, the equation for that plane is z equals 0. Just like in 2D, the equation of the x-axis is y equals 0. The equation of the y-axis is x equals 0. Well, in 3D, if you have z equals 0, it doesn't mean that you're a line, it means you're on the xy plane. And going back to the room example, where you're looking at these 3 sets of axes as the bottom corner of your room, the XY plane would be the floor. In 3 space, we also have, so the next key plane would then maybe be the XZ plane, the one that sort of connects X and Z axes together. And on the XZ plane, if you're a point on that plane, it just means that your Y has to be 0. And so the XZ plane similarly has an equation y equals 0. And then our last key plane is the YZ plane. So and that would be x equals 0. As long as your x is 0, you'd be on that plane. And then again, in the room analogy, the xy plane would be the floor, and then the xz and the yz planes would be the two walls. So one where the x value is 0, one where the y value is 0. So that's sort of my little intro to 3D. I think I was going to draw those planes all in separate pictures, but I tried to draw them all at once, but maybe that would have been helpful. So if you want to draw just the xz plane and put that note together, and just, or the yz plane. If you want to separate those out into different pictures, maybe that would be helpful. And then just pay attention to the diagrams, because I always have a debate as to it can be drawn either way. Usually always the Z's, this vertical looking axis, but sometimes people call this the Y and that the X. So just look at their diagram and see how it's drawn. You can draw it either way, it doesn't bother me. Okay, so now what we're going to do is learn how to actually draw vectors in 3D, because it's pretty tricky, but there is a way to do it so that it kind of works out. So we're going to draw the vector 4, 3, 2. So I'll keep it going this way with my x going out to the right. So 4, 3, 2. So that's the vector that starts at the origin and then ends at the point with a 4 for x, a 3 for y, and a 2 for z. And with that, I don't know where to put the other point. Just looking at this picture, it looks a bit crazy to me. So what I do instead is just we draw what's called a box diagram. So you're going to sort of frame the vector inside of a box where 0, 0, 0, so the origin, and the 4, 3, 2 are sort of opposite corners of the box. So I'm just going to draw some vector, and then I'm going to try and frame it in a box. So 4, 3, 2 is going to be sort of the front right corner of my box, and 0, 0, 0 is going to be kind of the back left corner of my box. Front right top corner versus back left bottom corner. So how I do that is sort of draw a rectangle on the front, draw a rectangle for the back, and then make a box to sort of give this diagram some shape. So now I can kind of visualize that that vector is coming sort of out of the page towards me. So that's the corner 0, 0, 0. And then this corner is 4, 3, 2. And so what I want as just an exercise is see if we can label the other. So that one's 0, 0, 0. See if I can label the coordinates of the other corners on this box. Oh, sorry. Just want to set it up as blanks. And that one down there, blank, blank. And I need one more set of blanks for that one there. So you can pause the video here, see if you can label the other corners of the box, and then unpause and see if you get the same as me. So I would start thinking here, if I think about this angle, this dot down in the bottom right here, all I'm doing is I'm dropping straight down below this point 4, 3, 2. So I'm keeping the same x and y, and now my z is 0. So one way to think about it is the top of the box all has z's of 2, and the bottom of the box all have z's of 0. So we can start to fill in the points one at a time from there. If I drop from 4, 3, 2, and I slide back along this side here, I am moving in the y direction. So I'm keeping my x, I'm not moving left to right in my picture. I'm keeping my x, I'm just sliding back on the xz plane, so my y value is 0 is another way to think of that. And so everything on the back of the box, so would also have a y of 0. So all 4 corners on the back of the box would have a y of 0. Oh, sorry, that's not pointing to this one. The origin is the other one down there, which already has the y of 0 filled in. So I've got y of 0 on this one, that one, that one. So I got my 4 y zeros there. The 4 corners on the front of the box, so these, hard to show you which ones I'm looking at, but those 4 on the front of the box all have a y of 3. So I can fill in the y of 3 there, there, and there. And then similarly now with the x's, everything on the right side of the box is going to have an x of 4. So these 4 points on the right side have an x of 4, and all the points on the left side have an x of 0. And then you can double check the ones that land on the axes. So the one on the x-axis only has x as a number and the other 2 are 0. The one on the z-axis has z as a number, the other 2 are 0. The one on the y-axis has y as a number, the other 2 are 0. So that's a way to keep track of that. So I'm going to get you to do the exact same thing in this next one. So represent the vector 3, 2, -4 with a box diagram like we just did. And remember the origin and the corner, the vector sort of corner of the box are on opposite sides of the box. So this one has a z of -4. So actually the box will now be below the xy plane. So the origin is sort of going to be on the top of the box and the vector is going to be on the bottom of the box, to give you a hint there. And then similarly, I'll get you to find the vector that connects the points A to B. Hey, there's a formula for that. And then represent the thing below as a single vector. And hey, guess what? It works exactly the way you'd want it to work. So see if you can do those 3 and then unpause the video and see if you get what I get. And so 3, 2, and -4. I'm just going to draw an arrow down here. But the key thing is that's going to be now sort of the bottom corner of the box. And the origin is now going to be on the top of the box. So I might start my 2 rectangles like that. Something like that. And down here is 3, 2, and -4 is my z, and the top is 0, 0, 0. And then similarly, everything on the bottom of the box is going to have a z value of -4. And everything on the top of the box is going to have a z value of 0. Trying to find spots to write my points. I think I got all my z's filled in. I think I've got blanks for all 8 points there. Everything on the right side of the box is going to have an x value of 3. And everything on the left side of the box is going to have an x value of 0. Back on the xy plane, sorry, the xz plane for these points over there. And then the front of the box, so these 4 points here are all going to have y values of 2, and the back of the box will all have y values of 0. So there we go. So I could draw really complicated diagrams to show that these work, but our 2D formulas thankfully all work in 3D as well, just the way you would want them to. So we're just going to do b minus a to get the vector that connects a to b. So that looks like 1, negative 22, and 7 if you do b minus a. And then representing as a single vector, so I'm going to multiply, do the scalar multiplication first. So multiply those scalars into the vectors. And then that looks like 12 plus 18, take away negative 5 would be 35. Negative 12 plus negative 6 is negative 18, and then take away 5 more is negative 23, I think. And then 8 and 30 is 38, and then subtract 10 is 28. So that would be my final answer there. And that formula sheet addition is a spoiler because I forgot to do that. It's like we forgot to find the magnitude of this vector here. So in order to do that, let's just pretend that we don't see the formula below. We're going to work with that right angle triangle. And we know that this side of that right angle triangle is 2 because that's the height of the box. To get this side that kind of cuts through the middle, we're actually going to use this right angle triangle sitting on the xy plane. So we get 3 and 4 for its 2 side lengths. And so that base along the middle, using Pythagorean theorem, would be the square root of 3 squared plus 4 squared, which would equal 5 if I equaled it out. But to see the formula, I'm actually not going to write it out like that. So to get the magnitude of u, then using the Pythagorean theorem would be that side plus the other side. So that bottom side squared plus the other side squared. And I wrote it out like that so that we can see that this squared here cancels the other square root, and you get 3 squared plus 4 squared plus 2 squared, which is the square root of 29, I believe, if you had all those together. So that would be the magnitude of that vector. But the nice thing here is sort of our 2D formula was the square root of its components squared. Our 3D formula is exactly the same. So Pythagorean theorem kind of works in 3D the exact same way it does in 2D. You end up doing the square root of now all 3 things squared and added up instead. So that's a quick way to get the magnitude of a vector in 3D, and that's something you should add to your formula sheet. So if your vector is a, b, c, then its magnitude is the square root of those things squared and added up. All right, so for consolidation, what do you know for sure about coordinates of points if they're on the x, y, and z axis? I talked about that at the start. What are the 3 main planes? So I'm talking about the xy, the yz, and the xz planes there, like I did at the start, and then their equations. So I talked about those at the start, and then the practice we'll do in class.